Welcome to the next iteration of our networking and I've gotten it backwards. Systems and networking seminar series, and I'm really happy to introduce Anirudh Shivara.
Yeah.
Thank you for helping me with that. Anyway, he's going to talk about programmable routers, and which is really hot area, maybe even the hottest area in networking today.
Thanks, Tom. Yeah, thanks all of you for coming, and thank you for having me here. So I'm Anirudh. As Tom said, I'm an assistant professor at New York University's Computer Science Department. I'm going to be telling you about how we can design routers that are both fast and programmable. Okay, so let's start with some sort of 101 network architecture, this kind of stuff that's taught in a graduate networking class. So the traditional wisdom with network architecture that sort of was adopted from the internet is to have simple routers and move most of the complexity to the endpoints. There were good reasons why the internet adopted this approach. Among them was the ability to support new networks by minimizing the amount of work that needed to be done on the routers, so that it was very easy to attach new networks to the internet. And in many cases, the end host is the most appropriate place to implement new functionality, because that's the place that knows best. And the minimum functionality that was left to the routers was what the end host couldn't do, which was best effort packet forwarding. Okay, so this has sort of been almost like a dogma that's been adopted throughout networking for the last several decades. But today's reality is actually quite different from that pristine view where routers just do packet forwarding. So for both performance and security reasons, we're demanding much more from our routers. So a router box today supports things like access control, tunneling, measurement, and so on. Yet for all this, despite the increasing feature creep in routers, the fastest routers have typically been fixed function devices. This is because they tend to be built out of dedicated silicon, where features like access control and tunneling have been hardwired into the circuitry of the chip, and they can't really be modified by network operators. So the end result of this is that the rate of innovation in new router algorithms so far exceeds our ability to actually get things into these routers. So here's a timeline of fairly prominent router algorithms since the 80s. Many of these have demonstrated significant performance benefits in simulation or in like low-speed software router platforms. But if you look at this and ask what fraction of these are actually available on routers today, it's a pretty small number. And in many cases, the lag time between when an algorithm was first proposed and when it eventually made its way into a router has been quite large. The best example of this I can think of is ECN. The idea actually goes back to DECbit from the late 80s, but it was the late 90s by the time it got standardized and widely available in routers. Yeah?
So are any of those protocols being deployed by cellular carriers? Because for them, the network speed is a lot slower.
Yeah, that's a really good question. So not cellular per se, but Cordel and Pi are both available in wireless routers, in some wireless router firmware. And yeah, it's for exactly the reason that you said, because they can be implemented in software, and they just it's much easier to upgrade those routers to implement things like that. Yeah. Okay, so if you were a network operator running a network and you wanted to affect change in your network, what do you do if you can't change the routers? So one approach is to use what's called a software router. I'm using this as a catch-all term for a router that's built on any programmable substrate. It could be a CPU, a GPU, an FPGA, or a network processor, which is essentially a CPU that has been specialized for networking. Now, probably the most important figure of merit for a router, at least the one that determines its success in a marketplace, is the aggregate forwarding capacity in terms of the number of bits per second it can shuffle across its ports. So let's look at software routers over time and compare them against the fastest routers known at any given point in time. So in the blue line, we have software routers, and on the red dotted line, we have the fastest routers known at that particular point. There are really two takeaways from this graph. Up through the mid-80s or the early 90s, the software routers were in fact the fastest routers. This was because the forwarding rates at the time were modest, at most a few megabits per second. So you could take a mini computer or a server machine, write some software for it to do packet forwarding, and that was more than enough. Since the mid-90s, growing demands for higher and higher link speeds, mostly fueled by the explosive growth of the internet, have meant that the fastest routers tend to be built out of dedicated hardware that has been specialized for packet forwarding. And the result of this is that software routers today are 10 to 100x slower depending on which software substrate you're talking about. And as a result, they haven't found as much adoption, especially in the high end. There are regimes in which software routers are good enough, but at least in the high end, sort of in the enterprise and in data center networks, this performance gap is large enough that it's a pretty big compromise to pay for the benefit of flexibility. The other problem with a software router is the fact that they suffer from non-deterministic performance. Now, the performance of a software router depends on the particular server machine that you're running it on, how much memory it has, what its cache is, and so on. By contrast, if you buy a router from, say, Cisco or Juniper, if it's rated for 10 or 100 gigabits per second on, say, 10 ports, it will give you that performance even under worst case conditions, which is basically minimum size packets on all ports. Right? So that determinism isn't something that software routers provide. Yeah?
Is this graph actually an argument for specialization, that we don't need the flexibility? Because in the sense that you're just specializing to data center context for the Broadcom chips.
Yeah, so that's a good point. So ultimately, I guess, as you'll see through this talk, the goal here is to add just the right amount of programmability so that you sort of still specialize the hardware for the purpose of forwarding packets, but make it flexible to the point that it's useful without giving up performance. So yes, in a way, it is an argument for specialization. So it's much better to build a domain-specific programmable processor for networking rather than taking a CPU and repurposing it for networking. Okay, so my work, yeah.
Explain why some of the software solutions just couldn't keep up. I assume if you use some kind of, is this just inefficiency of FPGAs or other hardware that couldn't keep up with ASICs?
Yeah, so I mean, one solution to scaling software routers that works in some situations is to basically throw more software routers at the problem. It works until a point, until you don't have all these different software processors contending on the same piece of memory, but it also comes at a cost. It just takes up much more volume, takes up much more power relative to an ASIC. But ultimately, the reason hardware is so much more powerful is that you can exploit ridiculously large degrees of parallelism without paying huge amounts of power for it. So that's the reason there is this performance gap. Like the reason specialization in hardware gives you performance benefits is because of parallelism at its core. Okay, so this talk is going to be about how we can have the best of both worlds to an extent, which is basically the performance of the fastest routers today endowed with some amount of programmability that makes sense to the router domain. Okay, so the problem with hardware routers today is we've taken fixed features and baked them into the hardware of the chip, and so you can't change these afterwards if you change your mind. Instead, we're going to be looking at what primitives we can put into the hardware chip so that they can be repurposed into features as required by the network operator or even the router firmware writer. And this allows you to sort of innovate on features at much more rapid timescales. Okay. So to give you a sense of what my contributions are, let me first describe what a router chip looks like at 10,000 feet. At a high level, packets come in from different ports into a pipeline. So this pipeline is going to carry out some transformations on the packet, like maybe rewriting the header fields and like writing the destination, the output port based on the destination address and so on. Then there's a scheduler where packets sit around if there are more than 2 packets destined to the same output port. And then once packets are dequeued by the scheduler, they make their way through an egress pipeline before they depart. So within this picture, I'll talk about 3 pieces of work. The first one is a system called Domino, which allows us to program streaming algorithms at high speeds that approach these fast routers. And by a streaming algorithm, for the purpose of this talk, I mean a router algorithm that processes packets in the order that they arrive. It does a bounded amount of work per packet. So you can't have a for loop with an indeterminate loop bound, and it maintains a bounded amount of router state when doing that work. So you can't maintain an ever increasing log of the number of packets. So that's the class of algorithms, and we'll look at what the right instructions for programming these streaming algorithms are and how to program them in software. Then I'll talk about how we program the scheduler, which is the part of the router that decides which packet to transmit next when there are multiple packets waiting for transmission at a particular output port. Then depending on how much time I have at the end, I'll cover this last system called Marple, which allows us to do programmable measurement of statistics on a per flow basis. So this could be as simple as a counter, but it could even be more flexible statistics such as maintaining a windowed average of a certain quantity or an exponentially weighted moving average. And I'll talk about an interesting algorithmic idea that allows us to do this in a manner that scales to a large number of flows while still running at the speeds of the fastest routers today. Ultimately, the message here is that it's possible to have both performance and programmability so long as you narrow your focus to specific classes of router functions. So it's this sort of specificity in focus that allows us to have both, and it does come at a cost. So the substrate that we're building here is not Turing complete. You can't run arbitrary programs on it, right? But we hope that for the specific classes of functionality we pick, it sort of hits the sweet spot, being providing enough programmability within functionality that operators care about without sacrificing performance. Okay, so let me start with the domino work. So our goal here was to be able to program streaming algorithms at high speed. So this is a fairly broad class of algorithms. It includes things like in-network congestion control like XCP and RCP. It includes measurement algorithms like sketches. It includes data plane load balancing algorithms, buffer management algorithms such as red and blue, and so on. Okay, so let's first start with what the right hardware for programming streaming algorithms should look like. Let me start with a more detailed description of a fixed function router pipeline, and then I'll talk about how we can make that programmable. Okay, so to start with, you have multiple ports on a router. Bytes come in on each of these ports. They're handled by a parser that turns these bytes into what's called a header vector, which is basically a partitioning of these bytes into different headers. So maybe the first 12 bytes or so go into Ethernet, the next 20 bytes or so go into IP, the next several bytes go into TCP. This header vector then makes its way through an ingress pipeline, and this pipeline is made up of a bunch of stages, and each stage is structured around this concept of match action processing, where the match unit in each stage filters out packets of interest, and the action unit carries out some packet transformation on those packets of interest. So as an example, the match unit could say match on all SSH traffic by looking at TCP port 22. The action unit could say set a priority bit on those packets to prioritize forwarding those packets. At the end of this pipeline, there are a bunch of queues that hold transient packet bursts if you have more than one input port trying to send to the same output port. There's a similar egress pipeline for modifications after packets have been dequeued, and then packets go out. So in a fixed function router today, these pipeline stages are dedicated to some fixed functionality such as forwarding, access control, and so on. Now the important thing to know about this pipeline relative to a processor pipeline is that it's a deterministic pipeline that supports a throughput of 1 packet per clock cycle, which is typically a gigahertz, a nanosecond, or a clock rate of a gigahertz, under worst case conditions. So even for the smallest packet size, it's going to support this throughput. So you can imagine that in steady state, each pipeline stage sort of sends one packet to the next one and receives a packet from the previous one every clock cycle. Now this determinism leads to two sort of characteristic features of a router pipeline relative to a processor pipeline. The first is that state is local to an action unit. So if you have any state that is being maintained by the action unit, the simplest example is a counter that counts packets going through the router. That state must be local to an action unit, because if you have state that's shared by action units, you need what's called multi-ported memory to allow multiple different action units to basically access the same piece of state. And that kind of memory degrades performance either because you have to time share the single ported memory across two different entities, or it results in an increase in area, right? So because of these reasons, state is local to action units. Yes?
So this state is static, is logically partitioned or physically partitioned?
Yeah, so in our programming model, which I'll talk about in a few slides, the programmer thinks of it as state that is just maintained throughout the pipeline. The compiler physically partitions it into state that goes locally into each action unit.
I think like the physical implementation should always like be multiple ports. Like this partition should only be implemented as a logical partition.
No, so physically each memory has a single port. So in these routers, each memory physically has a single port that can support a single read and a single write per clock cycle. With the exception of some memories in the scheduler, because once you start scaling this up further, you can have multiple pipelines. So the scheduler alone might have multiple reads and a single write, multiple writes and a single read per clock cycle. But in the pipelines themselves, it's always single read, single write. Okay. So the second sort of characteristic feature of these pipelines is that the action units are heavily constrained to sort of support this throughput of one packet per clock cycle. So this is sort of what at its core leads to the non-Turing completeness of this substrate. You can't do arbitrary things here. So that's a fixed function router pipeline. Let's look at how we make it programmable. Okay. So our unit of programmability is this notion called an atom, which is a combination of local state plus some action unit that operates on that local state, with the constraint that the computation is simple enough that it can handle a new packet every clock cycle. So this is how we specify the instruction set of the underlying hardware. Now the reason we use a different term atom here instead of just calling it an instruction is that unlike say x86 or ARM instructions, there's this constraint throughout the design process when the substrate is being designed to ensure that the atom finishes within a clock cycle, and state updates within this atom are atomic. Okay, so that's why we use the term atom. Now if you look into one of these, here's an example atom which takes a piece of state x and either a constant that has been supplied by the programmer or compiler, or a packet field, and adds either the constant or the packet field based on the setting of a 2-to-1 mux. Okay, this is a really simple example of an atom. And it's constrained in the following sense that the input to output latency on that atom is 1 clock cycle, so that it can handle a fresh input every clock cycle. Now this may not be necessary for all atoms. It's a sufficient design criterion which we use to sort of simplify the design of these instruction sets. Now in practice, you would have multiple parallel atoms operating on different slices of the packet header, and at any clock cycle you can imagine different slices of the packet header being operated on in parallel in lockstep by these different atoms. Now the important thing to note about the substrate is that what atoms you have dictates the algorithms that the router can support. So this is very unlike a CPU, where so long as your code is syntactically correct, your compiler will compile all code, but the runtime performance will depend on the complexity of the code. Here on the other hand, the compiler will only compile some forms of code, but all the code that does compile will run at the full line rate of the switch. And what determines what code does and doesn't compile? That choice is made by the atoms. Basically, if you have an atom that can't read a piece of state x, add something to it and write it back, then you can't implement an algorithm that has a sketch at its core that makes use of a count operation, assuming you want to implement the algorithm exactly. So if you want to approximate the algorithm, this doesn't hold, but if you want to exactly implement the algorithm, it depends on what atoms are supported in the underlying hardware.
Stage, all the atoms do the same computation, like a SIMD model.
Well, no, not necessarily. So it's more like a VLIW architecture where each of these things can be programmed independently. So yeah, they don't need to do the same computation. Okay, so let me describe the overall workflow for a programmer programming this kind of substrate. So the programmer specifies the algorithm in this high-level transactional style that we call a packet transaction. And the programming model for the programmer is quite straightforward. On every packet, there's this transactional body of code that executes from start to finish for that packet. It may end up updating some state in the process, and only then does it move on to the second packet and repeats the same process on the second and the third and so on. So at least the conceptual model for the programmer is that they're running on this extremely fast single-threaded router that's processing one packet at a time without any overlap in processing across packets. Now, to write in individual statements within a packet transaction, we developed a domain-specific language called Domino. The major restriction in the language is that there are no for loops, because there is no easy way to compile a for loop with an unbounded iteration count onto a switch. And there are other restrictions, such as you don't have gotos, you don't have memory allocation, and so on. So this is a simple packet transaction that basically counts from 0 through 9 and samples every 10th packet going through the router. Okay, when the programmer feeds this into the compiler pipelines this code to match the underlying execution model of the hardware. And the goal while pipelining is to extract out these atomic components. And the guarantee is if that each of those components execute atomically and pass off results to the next stage, it's equivalent to a transactional execution of the original algorithm. So in this case, the compiler figures out that the first stage needs to read, count, and update it, and the second one sets packet.sample based on the old value of count. So in the next step of the compiler checks these pipeline stages against underlying atoms, and we use program synthesis here to check if there is any way to instantiate those atoms' configuration settings so that they can implement the pipeline stage. If so, it basically spits out a pipeline configuration. It's possible that the underlying atoms can't support what each of these pipeline stages require, in which case we reject the code. Okay? So I'm not going to go into any detail with respect to the compiler algorithms. I'm happy to talk about those offline. But I'm going to speak about what we did once the compiler had been built. And the major sort of takeaway from that exercise was designing the first instruction set for streaming algorithms at these speeds. And I'll show you how we do that. Okay, so here's the high-level workflow for designing an instruction set using this Domino system. We start out with a specification of the algorithm and the hardware. Right? The algorithm is specified in Domino. The hardware, we have a restricted language to specify the atom and a pipeline geometry, which is how deep is the pipeline, how wide is the pipeline. Okay? We feed it to the Domino compiler, which tells us whether the code compiles or not. Invariably, first time around, it doesn't. So it means something is wrong. Either your atoms aren't expressive enough or you don't have enough of those. So you go back and change one or both, right? And you then repeat this process until you're satisfied that the algorithm, until the compiler tells you that the algorithm can be implemented using the atom and the number of atoms that you've provided. Once you've done this, you move on to another algorithm and repeat this process until you have either one or a set of atoms that can implement as many algorithms as you care about. Okay?
Do you care about the number of stages? Because you can have one algorithm that requires 10 stages, and all the rest only require 2, and then it becomes really hard to allocate, memories for each of the stages.
Yeah, I mean, we do care about that. So, in our evaluations, we sort of saw that we needed 10 stages, stages that were 10 atom wide and 10 such stages, so a total of 100 atoms. But at a broader level, that isn't the biggest bottleneck here, because having more atoms is actually quite cheap, but building richer atoms that finish within a clock cycle turns out to be the bigger rate limiting factor.
Because there could be multiple solutions. So my question is, how do you select them? What is the criterion you use to select the right one solution out of this?
Yeah, so right now this whole thing is completely manual and ad hoc. We're just looking for a correct solution. We're not looking for the optimal atom in any sense. Yeah, so yeah, we don't have like a way to maximize like the goodness of the atom that we've picked. So right, at least currently we just pick a set of atoms that works. Yeah. Okay, so let me talk about an interesting conceptual distinction that we sort of realized when designing these instruction sets, and that gets to the heart of why instruction set design for these routers is a hard problem. Let's say you have a stateless operation where you take 2 packet fields, subtract a third, and write it into fourth. This is actually pretty straightforward to do using a hardware pipeline. You can have one instruction basically add f1 and f2, and the second one subtracts f3 from the temporary variable, and this way you can implement that entire compound operation. Okay, so this is what happens when packets flow through. This is more generally true. If you had a purely stateless operation, you can take the expression tree for that operation and then break it up into these pairwise operations and chain them together in a pipeline. And it has interesting consequences for instruction set design, whereas the hardware engineer responsible for designing the instruction set, you can design for all pairs of stateless operations between a pair of packet fields, say plus, minus, multiply, divide, shift, min, max, and so on. And when the compiler is presented with a complicated stateless operation, it can just break it down pairwise into these operations. At some point, you might run out of the number of pipeline stages, so that is a constraint. But you know, this, as I said earlier, we were looking for something that was correct. We weren't looking for optimal atoms in this particular project. Now let's look at the other extreme case of designing instruction sets. Let's say you had an entirely stateful operation that didn't touch packet headers at all, but instead incremented a packet field. Here's one attempt at designing an instruction set for this. The first instruction reads the stateful variable into a packet temporary. The second one increments it. The last one writes it back. Let's see what happens when you have 2 packets going back to back against this pipeline. So you have the red packet that shows up at this instant. A clock cycle later, it's picked up the value 0. Green has just shown up now. 1 clock cycle later, red has become 1. Green has picked up the old value 0. And this is really where the problem starts. 1 clock cycle later, X has been written the value 1, but green has now been incremented to 1 and ends up rewriting the value 1. But at the end of 2 packets, X should be 2 and not 1. So the way we fix this problem is to essentially design an atomic operation to do X equal to X plus 1 at the rate of 1 packet every clock cycle. And in general, this is true of stateful operations. It's hard to pipeline these operations, and instead you need to identify operations that touch the same piece of state and provide atomic support for these things in hardware. Okay, so that's really what makes this challenging. The more computation you have on a single piece of state that reads from a piece of state, does some processing on it, and then writes back to the same piece of state, the more complicated your instruction needs to be. Yeah.
Augment to this
Yeah.
point, which is the variable x lives in. You had discussed earlier that every memory has a single port for reading and writing, and that is guaranteed in that example just because it's what the earlier stage is doing the read and the later stage is doing the write. Is that the way to think of it?
In this one, yeah. So that turns out to be a second problem, which I didn't mention here. So notwithstanding the atomicity violation, this solution doesn't work for that reason as well, because you need multiporting here.
And there's an RMT switch you're not able to do there, as well as something like a DRMT kind of stuff.
Yeah, basically, I mean, any sort of multi-core processor, I mean, DRMT has that style of architecture, can do it because you can sort of access the same.
Just to make sure that the number of reads and writes which might be happening to the same memory is
Yeah, but this is not something.
That you can implement the wrong algorithm.
Yeah, exactly.
On DMR.
DRMT, great. Whereas in the RMT, you can't implement it.
Yeah, it gives you more flexibility, which means you can implement.
No, right. That's right.
Okay, so So let's look at a few specific computations and the atoms that sort of came out of those computations. So we've already talked about stateless operations like this, addition and subtraction on a pair of packet fields. So based on this, we generalized to a stateless atom that could carry out arbitrary binary operations. Again, typically seen binary operations. Then let's say we have these three patterns, one that writes a constant into a piece of state x, another that writes a packet field into a piece of state x, and another that reads from a piece of state x into a packet field. So this we could generalize into a read-write atom that allows you to either read the latest piece of state or write either a constant or a packet field into a piece of state, but nothing more. If you had x equal to x plus 1, you could generalize this to this accumulator atom where you can use a multiplexer to pick between either a constant or a packet field and add it to a piece of state x. And you can already see things are getting a little more complicated, and this example should illustrate that a little better. This is similar to the packet sampling algorithm that I described earlier. So if x is not 10, you increment it, otherwise you reset to 0. If you were to design an atomic instruction for this, it would look something like this. Based on a predicate, you increment or reset a state variable, and you can already see that the specification for this includes more muxes. You have to specify how complex the predicate can be, and so on. And stateful atoms can quickly get quite hairy. So this was the most complicated of the ones that we had. This is not meant to be readable. It's just to show you that it's complicated. This was a nested conditional accumulator, which is basically the conditional accumulator from the previous slide, but taken one step further. So you have 4 predicates that determine 4 different courses of action depending on the previous value of state. Okay. So we went through this process in a manual ad hoc trial and error basis, and we came up with a set of atoms. I talked about most of these. The last one is an atom that can take a tuple of 2 variables, and based on the old value of those 2 variables, it can write new values to both of those variables. Okay. And these were examples of actual networking algorithms that can run on hardware if they had these atoms. And we verified this by basically running our compiler by taking the atoms and the algorithms as inputs. Now so far, I haven't really told you whether these atoms can actually be constrained to run at the clock speeds that we require. So we took these atoms and then ran them through an EDA toolchain to target a recent transistor library. So the way this works is we basically wrote these as circuits in Verilog and ran them through these EDA compilers. And we saw that these all met timing pretty easily at about 1 gigahertz in a 32 nanometer transistor library. This is the size in micrometer squared of individual atoms. And if you take 100 of these laid out as 10 cross 10, then the total area overhead relative to a 200 mm squared baseline switching chip is actually quite modest. Now, it's always possible that in this iterative process we've ended up overfitting to particular algorithms of interest, right? Because if an atom doesn't work for a particular algorithm, we can just extend the atom until it does work. So because there was this danger, we froze these atoms, and much later, actually about 1.5 years later when I was wrapping up my dissertation, I took the old atoms and tried to compile a new set of algorithms to those old atoms whose design had been frozen. These were algorithms that sort of came up, these were algorithms written by other people. I did not know of these when I designed the atoms. And it turns out that the atoms actually generalized to unanticipated use cases as well. So, we don't have a theoretical proof that these atoms are general, but we have some empirical evidence that they support unanticipated use cases. Yeah?
Just a clarifying question.
Yeah.
I'm a little confused by one thing, which is that, we should think of your work as informing hardware designers as to what atoms to put into the switch.
Yeah.
Is the one we're thinking. But the thing which I'm wondering is that I thought that many of them provide almost like an FPGA-like functionality, which is even lower level, and in some sense they're kind of telling you what gates you can put in. So there's no reason to constrain yourself to this more bigger atoms as you might say, when you have access to those low-level things, which you can actually compose them in any arbitrary way you can. Is that the? And I'm just kind of.
So that's certainly true. So if you could do things with an FPGA, it's certainly a much more flexible substrate. The problem basically comes down to performance. The latest FPGA numbers I know of are from the Corsa switch, which is I think at around 640 gigabits per second aggregate. These atoms, which some of these designs were inspired by the instruction set in the Barefoot switch, those, I mean, that switch runs at about 6.5 terabits per second. So it's a factor of 10. So you're definitely right here. Like an FPGA has much more fine-grained programmability, can let you do much more, but it comes at the cost of performance.
Sorry, actually, my question was really like I think you might understand this better with the Cavium. Like they kind of let you specify the sort of the gates that you can use.
Right. It's a combination of muxes and lookup tables essentially.
Right. So in some sense, they are allowing you this low level, even lower level access. In some sense, instead of constraining you to this high level of operations. And as a consequence, you get to constitute whatever is necessary for your specific.
Well, okay. So again, I'm not totally familiar with the Cavium SDK, but if you look here, ultimately these muxes are similar to what he's talking about, and this is something that the compiler deals with when doing code generation. So we don't expect the programmer to go in and like say, okay, here this is which atom to use. Instead, the compiler will basically take those pipeline stages and use program synthesis to basically test it against all of these atoms. So the job of configuring these low-level muxes is the compiler's.
No, there's value from the compiler, and that would be pretty valuable for Cavium. And Cavium has no support for anything like this. But there's less of a need for designing the atoms per se from a switch perspective. We can take this offline.
Yeah, I mean, yeah, we can talk about this more offline, but I think ultimately it comes down to like how much flexibility do you want and what do you give up in performance. But I mean, happy to take this offline.
Can this be think of as an intermediate representation?
Which one? The atoms? The atoms are the instruction set itself. It's not an intermediate representation. So it is literally the instruction set of the hardware.
You were saying, gave the impression that it was about 1% of the chip area. I just wanted to understand that if your clocking is at a nanosecond and you're trying to run like a Barefoot switch at 4 terabits or whatever, you have to have multiple of these pipelines in parallel. So it's 1% per pipeline, and therefore you might need to have 10 or 15, 20% of your chip doing this, or?
That's a good question. So this is for 100 atoms. So we're agnostic here to whether they spread out across pipelines or within the same pipeline. What that changes is sort of the cost of the multiplexers. We have a slightly more refined analysis that basically adds a few tenths of a percentage on top of this. There's a bigger problem when you move to multiple pipelines though, which is not the area overhead, but the fact that an atom in one stage cannot be accessed by another stage. So you can't have state that is shared across pipelines. It's not so much the area overhead, like as I said, it's mostly a little bit more in terms of the muxes. But yeah, it does restrict the programmability quite a bit if these atoms are scattered across multiple different pipeline stages, because then you can't access state which is part of an atom in pipeline stage 1 from pipeline stage 2.
Well, I was, one of the models for that was to think that you were, running them on the input ports and that you weren't collecting switch level statistics. Like one of the questions is like, is it really essential for you to collect switch level statistics, or could you apply them just at the, could your programming model just restrict you to just input level programmability? I don't know if you looked at that.
So we didn't restrict the programming model to per input port programmability, because there are algorithms that want global state, like I guess sketches are one example where they just have one large array. But you're right, if you restrict yourself to input port level programmability, because each input port only belongs to a specific pipeline, you don't need this cross pipeline coordination, and that does allow you to basically multiple pipelines are not an issue at that point if you restrict yourself to per input port state.
Yeah. So in terms of that 1%, is that just about logic, or it does consider like SRAMs, for example?
So that is just logic. So, yeah.
Right. And so, are you keeping the same amount of SRAMs in your design from before? And this is just modifying the logic?
Yeah, so the amount of SRAM that you need is really a function of how many flows you want to do this kind of tracking over.
Because obviously, like usually these chips, they have 80% of SRAMs or things like that. Like it's really
about a third.
high, the amount of SRAMs that you have, I think.
Okay, so we don't consider SRAM in this analysis because I mean, the amount of SRAM that you need is mostly a function of how fine-grained your tracking needs to be. B, yes, I mean, that number can scale arbitrarily high or low depending, I mean, that the additional area overhead due to SRAMs can be arbitrarily high or low depending on how fine-grained you want your tracking to be. Yeah. Yeah.
Do you find any application that require like very complex atom that would not fit in like one cycle?
Yeah, so one algorithm that we couldn't implement was this algorithm called CODEL that had like a square root operation at its core. We weren't able to like basically squeeze it within a clock cycle. So there are algorithms like that, and to be clear, I mean the only algorithms we even tested out, so there was a little bit of self-selection here. We didn't like look at algorithms that run on middle boxes that do much more complicated processing on a per packet basis. So we had reason to believe that these things would compile. So we weren't even targeting much more complex algorithms, but there are algorithms that don't finish within a clock cycle.
But for the ones that you did show, those can run in one clock cycle.
Yeah, those can run.
Wait, actually, the interesting thing is that it's not just the complexity of the work, but but how? Suppose if you were to break them into transactions, what is the complexity of the transactions that you need?
Yeah, it's the complexity of the largest atomic component. Yeah.
You know, hopefully most algorithms won't have.
I don't know about that for sure because we didn't look at the kinds of stateful processing that happen on a middle box. So I can't say for sure that even the largest atomic components there will finish within a clock cycle. Yeah, certainly if you want to do some crazy floating point operation on a piece of state, then you can imagine the circuits becoming large enough to violate a nanosecond on the critical path. Okay, any other questions? Okay, so I'll next talk about how we program the router scheduler. This is the part that determines which packet to transmit next when you have multiple packets waiting at an output port. But first, why care about programmable scheduling? Now it turns out that depending on what performance objective you have for your network, you might want different scheduling algorithms. For instance, if you're a multi-tenant data center operator and you want to isolate one tenant from the other, you might want something like fair queuing. If you were a single tenant who owned the entire cluster and you have many short flows for RPCs, you probably care about shortest remaining processing time. And it turns out using the wrong algorithm can hurt your performance significantly relative to using the optimal scheduling algorithm for these purposes. Now the status quo today is a menu of schedulers that are baked into the switch hardware. So you can configure coefficients on these schedulers. So if you're doing weighted fair queuing, you can configure the weights, but you can't program a new algorithm from scratch. Now, why is programmable scheduling hard? There have been several scheduling algorithms that have been proposed in the literature over the last several decades, but there's little consensus on the right underlying primitives that capture all of these scheduling algorithms. So there's little consensus on the right inherent structure underneath these scheduling algorithms. So if you don't have that kind of primitive, this is a practical issue because the scheduler has tight timing requirements where you have 1 nanosecond NQs and DQs every nanosecond. So you can't punt on this problem and just use a general purpose substrate like a CPU or an FPGA. Yeah.
Remember there was a one paper which is saying in NSDI, which is saying that you only need one primitive for packet scheduling in the
and you can emulate every possible.
Yeah, so there are, so that was the universal packet scheduling work, and at its core, it uses a priority queue, which as you'll see is similar to the primitive that we have here. So in that sense, we're saying the same thing. The primitive here is a priority queue. The primitive in their case is a priority queue as well. That said, UPS is strictly limited relative to this kind of scheduler because, I mean, for the simple reason that they assume a model where only the end host can initialize the packet headers and the switches can't reinitialize or rewrite the packet headers, and that does reduce their expressiveness relative to this. For instance, they can't do non-work conserving scheduling. They can do fair queuing, but only at much more coarse-grained timescales. But the core idea of using a priority queue, which I'll talk about in a few slides, is similar to UPS. Okay, so we need an expressive primitive that can run at high speed. And to get at this primitive, let's start at the beginning. What does a scheduler do? It decides on the order in which packets are transmitted, which is the case for work conserving schedulers, and the time at which packets are transmitted, which you might use for non-work conserving schedulers that choose to hold on to a packet even though there is spare link capacity. And these aren't mutually exclusive. You could have schedulers that control both. So how does a scheduler in a router today work? Packets come in, they're classified by an ingress pipeline, they go into one of several queues, and then there is a fixed set of schedulers sitting off on the DQ side of these queues that implement things like prioritization between different queues, round robin across different queues, rate limits, and so on. Now, our first instinct to make this programmable is to turn the scheduler into a programmable DQ function where you can write your own logic to specify what happens on a DQ, maintain your own state, and so on. The problem with this approach is there's very little time between consecutive DQs on an output port at high line rates. So this is about 5 cycles at 100G, and this number will only shrink as we go to 400G on a single link. So the design question that we asked ourselves is, can we refactor this scheduler design by pre-computing as many of the programmable operations of the critical DQ to DQ path and moving them to the NQ side instead? So the primitive that we came up with does exactly this, and it builds on this observation that in many schedulers, the relative order of packets that have already been buffered in the system doesn't need to change even when new packets come in. So if packets have been placed relative to each other, they might have to be moved to make room for a new packet, but the order relative to each other, relative to the old packets, doesn't change. In other words, you can find a packet's place in the scheduling order at NQ time and just leave it there. So a natural primitive for this, which was first proposed as a theoretical construct in the late 90s, is something called a push in first out queue, where packets are pushed into an arbitrary location in a queue based on a rank, but always DQ'd from the head. At an API level, this is identical to a priority queue that you might be familiar from a data structures class. The reason we use the term PIFO is the term priority queue is a bit overloaded in the networking context to mean priority scheduling, while PIFOs are intended as a primitive for both work conserving and non-work conserving scheduling algorithms. So here's a cartoon depiction of how it works. Let's say you get a packet with rank 8. It goes between 7 and 9. So 13, 10, 9, and 9 didn't have to be reordered relative to each other, and the same is true for 7, 5, and 2. Okay, so how do you build a programmable scheduler on top of this PIFO? Really, the only thing you can program in a PIFO is the way the ranks are computed. The idea of keeping ranks sorted and dequeuing from the head is fixed. So by pulling out the rank computation and having it be controlled by a user-defined program, we can make the scheduler programmable. That's the key idea here. So at a design level, there's this decomposition between the fixed logic of keeping packets sorted by rank and the programmable logic of computing the ranks for the packets. And going back a few slides, this is how we sort of move the programmability outside the DQ path to before the NQ path, so that it can be pre-computed and it doesn't have to be on this tight critical path. So where do these two components go on a real switch? The PIFOs replace the standard first in first out queues. The rank computation runs on the ingress, And in fact, it can be written as a packet transaction, and we can use the Domino compiler to compile the rank computation into a pipeline of atoms. So let me give you two quick examples of this. The first one is the work conserving classical fair queuing algorithm. This is the start time fair queuing implementation, where for each packet we track its virtual start time in an idealized fair queuing system, and that becomes its rank in the PIFO. At the end of this rank computation, we update the finish time for a flow to the start time of the packet plus its length, and this is how we do start time fair queuing. As an example of a non-work conserving scheduler, we can do token bucket shaping, where we have the rank computation update the tokens at a certain rate, and this is maintained as part of state in the pipeline. And then the packet's absolute wall clock departure time is set to either the current time if there are sufficient tokens, or some time in the future when it would have made up the shortfall in tokens. And again, once the packet has been sent out, you decrement the tokens by a certain length, and then the packet's rank becomes its absolute wall clock send time. Yeah.
Does the switch then just sit idle even if there are packets in the queue and like does not transmit it?
Yeah, I mean, if it's a non-work conserving algorithm, then yes, the switch will sit idle. Yes. Okay, so this is all PIFO in the abstract. Can we actually realize this in hardware? So we set out to meet some performance targets that are typical for a shared memory router today. So these were numbers based on the Broadcom Trident 2 from a few years ago. Yeah.
How you would implement the non-work conserving aspect of this?
Yeah, so it just sits around at the head. So the packet pointer just sits around at the head, and basically if the time for the packet hasn't arrived yet, so at every instant you dequeue and check. If it's a non-work conserving algorithm, once you dequeue, you check ahead. Yeah. So I guess in practice you can't put something back if you've dequeued it, so you just keep it in a holding area. But the packets themselves are stored in a separate sort of packet memory.
That was the part that
Yeah. Okay, so these were sort of the performance specs that we tried to reach with the PIFO hardware implementation. The important thing here is this is a shared memory router where the scheduler's logic and the scheduler's data structures are shared across all ports. So you don't have to further multiply area overhead numbers by the number of ports, because the scheduler is just one digital circuit that's shared across these ports. Now, the naive solution to building a PIFO that accommodates 60,000 packets, which is the worst case scenario for one of these routers, is to basically have 60,000 parallel comparators, and when a packet comes in, you compare it in parallel to each of the 60,000 elements. You get a bitmap that tells you where it's greater and where it's less than the current element, and this bitmap will have a single 0 to 1 transition which you can find and drop the packet in the right location. Now the problem with this is building that many comparators is a layout nightmare in hardware. So instead we exploit this pretty natural observation from the domain of networking, where for most practical schedulers you're really just scheduling across flows, because for other reasons you don't want to be reordering packets within a flow anyway, right? So whether it's start time fair queuing or whether it's token bucket shaping, the ranks of a packet naturally increase across consecutive packets within a flow. So it's sufficient to sort the 1000 head packets alone, right? One from each flow. Now, this is still pretty far away from the ideal PIFO of 60,000 packets. So in the ideal case, you could have one packet from each flow and you have 60,000 packets, so 60,000 flows. So we were able to push this to about 2K, at which point it started sort of violating timing. But for this 1K implementation, so 1K flows, which is useful enough to support programmable scheduling across, say, VMs belonging to all host machines under a particular rack, the area overhead relative to a 200 mm square baseline chip is about 4%. Okay. So yeah, I just want to briefly touch upon some broader impact that this work has had beyond the papers themselves. So there's several ideas from Domino that are now part of P4. This happened over a course of a couple of years because I started the Domino work as an intern at Barefoot, and I started attending the P4 language group design meetings. So packet transactions are now available as an atomic annotation in P4, where you can sort of mark off an entire block of statements as atomic. Previously, actions within P4, the statements within an action would execute all in parallel. This was changed to sequential semantics based on some early experience we had with the Domino project. And over time, several of the high-level constructs from Domino basically migrated into P4. So yeah, at this point, P4 16 more or less has everything that we had as language features in Domino. Okay, so that was one, and then there's been some industry interest in PyForce and in Domino's compiler techniques to go from packet transactions to the underlying hardware. So to conclude, I'd just like to reflect on what I see as the future of this field and like my own future work that I'm thinking of in this space. So if we take a step back, router programmability benefits two sets of people in industry. Okay, there are the router vendors, the likes of Dell and Arista and Cisco and Juniper and so on. And they benefit because you can now add router features in firmware, respond to customer requests faster in a matter of weeks as opposed to years. You can fix bugs faster in firmware than in hardware. And overall, that simplifies the job of a router vendor considerably. And then there are the network operators, the likes of Google, Microsoft, and other enterprises, where they can add new features and customize the network to their needs without having to haggle with the chip manufacturer to put in a new feature. And this haggling has long been a problem. Like VXLAN and NVGRE were examples of protocols that the network operators wanted, but it took many, many years to standardize them because the chip vendors had to get on board and so on. My sense is programmability will happen for the first reason sooner or later because there's just too much benefit to it for a router vendor to fixing bugs in firmware, adding features in firmware, and so on. And this is especially true now because the costs of building hardware in the more recent transistor nodes is only going up, right? So the sense I get is that for to the extent possible, if you could replace features in the chip with primitives that you could sort of turn into features only later, that definitely helps the router vendors. On the second point, I'm not yet sure, right? It's something where, for the most part, in many companies, people have gone to the point of pulling things out of the routers, and now that they're programmable, there needs to be a little bit of a mindset change to put things back inside. So this actually ties into some future work that me and my colleague Arijit Panda, who will join at NYU in the fall, are working on, which is let's assume fast and programmable routers can be built, and I hope to have convinced you through this talk that that's not out of reach. And the question then is, how should we use them, right? And there are already some commercial products that do this. Barefoot's Tofino switch is one. Cavium has a few products. And more specifically, in this new age of programmable silicon inside the networks, what stays on the end host and what should be moved into the network? And how do we sort of reason in a principled manner about both the benefits of moving functionality into the network and the costs? Because you're sort of dealing with a new substrate here. There's the cost of managing the substrate. And ultimately, the network and the switches are a shared resource. So you want it to benefit multiple applications. So I'd like to acknowledge all of my co-authors on this work, and I'm happy to take questions.
So that programmability stuff that you're saying then implies that we will have more network specialization.
We will have more network?
People with specialized network.
Yeah.
Right? Because these network operators, they will specialize the network according to their needs, right?
Yeah, I mean, at some point in the future, I don't know how soon that will happen. Yeah. Yeah, so in many cases, an operator might decide that they only have need for one or two features, and so they can use all the memory for those features instead of whatever is the standard model that the chip manufacturer has in their head. So yes, you can definitely specialize and tune the network equipment to your needs.